Okay, so it's called one-way Anova testing. And Anova stands for analysis, so the AN is analysis. The O is for of, and the VA is for variance. Okay, so analysis of variance. It's called one way because it's dealing with one independent variable. Okay, but kind of talk about, give you a scenario here that I think is the best way for describing what this Anova testing, what it's all about, what it does for us. So the medical researcher is analyzing the effectiveness of 3 types of pain relievers and wants to determine whether there's a difference in the mean lengths of time it takes 3 medications to provide relief. So the idea, if I've got Tylenol, maybe Advil, and ibuprofen, and I want to know, okay, is there really a difference in what I take? Okay, let's say that we're using the same milligrams on each of those. Is there a difference in the meantime, or can I take Tylenol in lieu of Advil in lieu of ibuprofen? Okay. Says to determine whether such a difference exists, the researcher can use what we call the F distribution with a technique called analysis of variance. It says because one independent variable is being studied, the process is called one-way Anova. Okay, so I'll give you a real quick. I think GeoGebra provides a visual of an F distribution, maybe. Distributions. Okay, this is what our F distribution looks like. Okay, and it changes per degrees of freedom. So let's say if we go degree of freedom 7, let's make this like 5. Okay, so you can start to see that it's a skewed right distribution, correct? Okay. And when we look at comparing variances, that's the distribution we get. But the key concept here is that we're going to basically what happens is now our null hypothesis, as we've been working previously, our null hypothesis has always been comparing 2 things, right? You compare maybe 2 means from populations, or maybe we would go back to chapter 9 where we're just saying using hypothesis testing for 1 mean. Okay, chapter 10 is working with 2 means. Okay, so there's mu sub 1 equals mu sub 2. Okay, now it's going to be working with 3 means. Okay, or 4 or 5 or 6, which logically, hopefully, you realize that, well, that's going to be kind of hard to do, maybe some algebra on that, because like an equation like this, mu1 equals mu2 equals mu3, how do we, turn that into mu1 minus mu2 like equals 0, like we've done with 2 means? Okay, but this is what our null hypothesis is going to always look like. It's going to be however many objects you're looking at, how many different population means you're looking at, and you're going to set them all equal to each other. Okay, because we want to see, are they the same, or like the scenario says, is there a difference that exists? Okay, so the key concept is that we're going to have 3 or more populations. Okay, you're not going to know the population means. Okay, so the F distribution is used for comparing or conducting hypothesis testing with 2 variances, variance sub 1, variance sub 2. Okay, this is how you're going to write all Anova hypotheses. Okay, mu 1 equals mu 2 equals mu 3 equals mu 4 equals mu 5 equals mu all the way through k. Okay, so however many, in our situation, the scenario I started with, it'd be mu 1 equals mu 2 equals mu 3. Okay, if I was trying to see if there's a difference between 4 medications, it'd be mu 1 equals mu 2 equals mu 3 equals mu 4. Does that make sense? Okay, so we're comparing 3 or more. Okay, the alternative hypothesis is always going to be written in words like this, where it says at least one mean is different than the others. Okay, at least one mean is different than the others. The one thing about Anova hypothesis testing is that it gives you the conclusion gives you a starting point. Okay, if we reject the null hypothesis, then the alternative hypothesis is then we have evidence for that to be true. It does not specify which one is different. Okay, so for instance, if we look at this scenario and say, okay, let's say we got Advil, Tylenol, and ibuprofen, and we say that the null hypothesis is rejected. So we would say that one of those does have a different time interval for providing relief. It does not pinpoint which one, though. Does that make sense? So it gets the ball rolling and saying that there is a difference, but then we would have to do further testing to realize where the difference resides in which medication. Okay. It says, why is it called analysis of variance? And this is because we're analyzing how the means from different populations vary. Okay. So how the means vary. That's why we call it analysis of variance. Okay. It says, when rejecting the null hypothesis, you are stating that one of the means is different. However, without further statistical testing, you cannot decipher which mean is different. And that's what I just talked about, not being able to pinpoint which medicine is different. Okay. These are the conditions that we need to have met, which are very similar to the conditions that we've seen in the past for other tests. We must have samples that are randomly selected, okay, from a normal distribution, normal population. Samples must be independent of each other, okay, so that's consistent with a lot of things that we've been talking about, and each population must have the same variances, okay, and that's probably pretty much going to be assumed or provided in the problem that you know that to be true, okay. So the test statistic for one way Anova test is the ratio of two variances, the variance between samples and variances within samples. Okay, so that's kind of a hard thing, and hopefully I try to explain it the best I can when we get into some specific questions. But it says the variance between samples and the variance within samples. So what's going to happen is maybe each row in this classroom is a sample. Okay, so let's say this row back here, sample 1, this row here, sample 2, sample 3, sample 4, sample 5, okay? When we say the variance within the samples, that'd be looking at this row and looking at their 5 pieces of data and seeing how those 5 pieces of data vary. Does that make sense? If I look at the variance within this sample, okay, it'd be how these 3 values differ. Does that make sense to everybody? Okay, and then do that for samples 3, 4, and 5. That's looking at variance within samples. If I look at variance between samples would be how does this variance, the mean essentially of this row here vary with this one. Does that kind of make sense? So now I'm comparing the samples to one another. Okay. It's kind of confusing, but the formulas will hopefully be explicit enough to explain or to do that for us, okay, to demonstrate that variance between and within. But the test statistic is variance between samples divided by variance within samples. So the variance between samples, which is a lot. Now you can look through 5 different textbooks, and you'll probably see 5 different notations for some of this stuff, okay. Our textbook, and I try to stay consistent with Math Excel, says MS, okay, so MS sub B, okay, says the variance between samples, and the B represents between, measures the difference related to the treatment given to each sample and is sometimes called the mean square between. MS stands for mean square, B sub B stands for between, okay. So that's the variance between. The variance within samples measures the difference related to entries within the same sample. So that's the idea of looking at the 5 people in that first sample and finding the variance within those 5 data points. And then the second sample, finding the variance within maybe those 3 data points. Okay. So the variance within samples is MS sub W, and sometimes that's called the mean square within. Okay. Says if the conditions are satisfied, then the sampling distribution for the test is approximated by the F distribution, and the test statistic is found using this. It's the ratio of the mean square between divided by the mean square within. And the way I remember that is the B and W are alphabetical, so B up top, W on the bottom. Okay, and that'll get you the correct ratio. The F distribution is a lot like the T distribution in regards to the fact that it's a family of curves. Now it's a skewed distribution, but because it's a family of curves, we're going to have degrees of freedom again. Okay, and we'll talk about these as we move on. But it says degrees of freedom sub n is equal to k minus 1. And degrees of freedom sub d is equal to n minus k. Okay, so k is the number of samples. Okay, k is the number of samples, and n is the is the sum of the sample sizes. Okay, so we might have 5 samples. Okay, so that would be k. And then n is the sum of all the things that are in those 5 samples. So let's say that this classroom, like going back to the rows being our samples, we'd have 5 samples. So k would be 5. Okay? But n then would be, the 5 people in sample 1 plus the 3 people in sample 2 plus the 2 people in sample 3 plus the 5 people in sample 4 plus the 5 people in sample 5. Does that make sense? Okay? So it'd be all the essentially the participants involved in the study. Yes, please. We're going to use both of them. Okay. So what's going to happen? We're going to give you a lot of formulas here, and we're going to do this one time by hand because doing it that one time, we're probably going to make mistakes. Right? It's very messy. Okay. So when we get to using something like StatCrunch or Excel, I don't think I have to look, but I don't think GeoGebra has this ability. We're just going to type the information. We'll gain the information, gather it from our scenario, write our hypotheses, type the data in, let the programs do all this work in the background, and then we analyze that result. All right. So let's find the test statistic for a one-way ANOVA test. Here's the following procedure. You agree that's a lot of stuff? Okay, so that's why we're going to do it only one time. I don't want you guys to spend a whole lot of time writing it down right now in class, but it'd be wise, I think, to maybe print this off. Again, doing it together in class one time. When you get to your homework, my thought is, you're going to use your StatCrunch or Excel to help progress through that. Now, in your homework, there might be some tiered questions that ask you to find something that we call the grand mean, which maybe when you type the information into your programs, that doesn't show up. Okay, they might ask, so what I'm saying is that as you go through your questions and there, the 3, 4, 5 parts to them, some of those parts might ask you for some of those formulas there. Does that make sense? Okay. So it would be maybe useful to have those, but we're going to use, like I said, we're going to use our programs to help us ultimately get a final conclusion. Okay. So here it says find the mean and variance of each sample. Okay. So X bar, that's X bar that we've always known. Okay. That's the sample mean. So you're going to add up all your samples and then divide by all your objects in your sample, and you're going to divide then by how many you had. Okay, that's exactly what we've done. That's a formula from 4th grade math when you learn how to do averages. Add them all up, divide by how many you have. So that's your sample mean. Okay, your standard deviation, or I guess in this case the variance, is exactly the same as the variance that we've always found. Okay? It's the sum of each data point minus the mean squared all over n minus 1. Okay, so we'll do that for each sample. So where this becomes t, I mean, this alone, maybe not all that bad. There's, 8 or 9 formulas here. But what happens is that if I've got 3 samples now, I got to do this stuff 3 times. Okay. Step 2 says find the mean of all entries in all samples. Find the mean of all entries in all samples. That's called the grand mean. Okay. And it's denoted as X double bar. Okay. And what you do basically, so if we're looking at this classroom, these rows being 5 individual samples, we would add up all the entries from sample 1. We add up all the entries from sample 2, all the entries from sample 3, from 4, and from 5, and then we would divide by how many total things we're in. Does that make sense? So, if we're talking about that first scenario I gave you with the medications, okay, we would take the mean times for all the people that were in the sample that was attached to Tylenol. Then we would take all the people that were attached to ibuprofen and all the people attached to Advil. We'd find all those mean pain relief times, add them together, and divide by the sum of all 3 of those groups. Okay, so that's called the grand mean. So that capital N, it's relatable to this N. Okay, but let's kind of do it this way. Maybe this will make it easier to see. If we were to find the mean and variance of each sample, so we're going to have, let's say we have 3 samples. So then the mean of sample 1 would be the sum of the objects in sample 1 divided by the size of sample 1, right? If I had sample 2, the mean of sample 2 would be the sum of the objects in sample 2 divided by the sample size of sample 2. If I had sample mean 3, it's the same idea. The objects in sample 3 added together divided by the size of sample 3. When I get down here to this N, that N is equivalent then to the N1 plus N2 plus N3. It's adding up all the objects that were in N1, all the objects in N2, and all the objects in N3. Does that make sense? Okay. And then the sum of X here, using this scenario up there, would be X1 plus X2 plus X3. Okay, that's the sum of all of the data points from each sample divided by the size, the sum of each sample. Okay. Step 3 says find the sum of squares between the samples. Find the sum of squares between the samples. What that means is that you're going to take the sum of, you're going to take N, which is the size of each sample. Okay, so I have to do this multiple times. I'll have to do it with this sample. I'll have to do it with the second sample, the third sample, the fourth sample, however many samples we have. So we'll put that in there. Okay, and then it's X bar, be the mean of each sample minus the grand mean, and then we'll square that. Okay, and if we're doing this by hand, this is probably going to be best computed with, I say do it by hand, but we'll probably use Excel to generate those and organize those for us. Okay, then we'll find the sum of squares within the samples. Sum of squares within the samples, and that gives me this formula here. Okay, and we'll go through, and this stuff will make a little bit more sense. I know there's a lot of nasty notation here, but n sub 1 minus I, so that will be the size of sample 1, or the size of sample 2, or the size of sample 3. We'll subtract 1 from it, and then multiply it by the variance of the corresponding sample. Okay, so that's SSW. So then the mean square between, okay, is found by taking that number right there and dividing it by our degrees of freedom sub n, okay, which that is equal to k minus 1. If k was the number of samples that we dealt with, okay. The mean sample, or sorry, the mean square within is found by taking this, okay, the square, the sum of squares within, and dividing by the degrees freedom sub d, and that was n minus k, to find the degrees of freedom sub d. And then our F statistic is taking these two values and putting them in a ratio, and that ratio then will be what we use to test our statistic, or test our hypotheses, okay? Pretty nasty, I think, okay? Says you will have, so the structure of what we are testing says you will have 3 or more populations. Say, let's say those 3, let's say we have 3 high schools in the area, and we want to determine if all of them are performing at the same level, but do not have the resources to test each and every student from each school, okay? So the following visual explains what ANOVA addresses. So let's say that we've got these 3 large schools in the county, okay? And we want to see, are they performing the same, or is one of them different, okay? So let's say school 1 has a size of 3,000 students. School 2 has a size of 2,800 students, and school 3 has a size of 3,300 students, okay? And we have no way of testing, what is that, about 9,000 students. We have no way of testing those, all of them, okay? And collecting the data and then analyzing the data, okay? But we might have resources to maybe analyze some samples. So the first school, we take 100 students and we test them. We randomly select out of this 3,000, 100 kids, and we test them on a standardized test, okay? We take school 2, we take 90 of them, okay, and we test them. And in school 3, we take 85 of them and we test them, okay? Now, it does not matter. Those n's do not have to be the same. They could be the same, okay, but lowercase n, the number of people that I sampled, does not have to be the same, okay? So these 100, okay, are, once we find their scores, once they take the test, we grade it, we find their scores, we take their average, that's going to be the sample mean sub 1 here, x bar sub 1. We take these 90, give them the test, grade it, take those 90 grades, and average them as one value. That becomes mean sub 2, okay? And then do the same thing for sample 3, and this becomes mean of sample 3, okay? It says all the formulas provided above are within our capabilities, and we will do the following example using them. However, most times, because of the tediousness, we will use Excel to do most of the work, okay? I don't know what happened here when I wrote this by hand, but it says ANOVA tests the variances between x1, or x bar sub 1, x bar sub 2, and x bar sub 3, which were these sample means. So it tests how this one varies from that one, and how this one varies from that one, and then how this one varies from that one. Does that make sense? And that would be comparing how all 3 of them vary to one another. So to decide, we test those to decide if mu1, population 2, and population 3 are the same. Okay? So, we'll stop there because there's absolutely no way in the next 8 minutes that we're going to get this done. Okay, this question done. So, tomorrow we'll come in, we'll pick up with this example right here. I've got a lot of the information already organized. I've got the structure of the steps that we want to go through organized. And then, so we'll do that one with that structure. But if you look at then the next one, I don't have that detailed structure, okay? I do have the things that we'd be looking for, like the grand mean, the mean square between, mean square within, but I don't have all those intermediate procedures that we would do to get those values. Make sense? So tomorrow will be very detailed in this first example, a little less detailed in the second example, and then we get to a third or fourth example, or we get to the homework. The ultimate question is reject or not reject. Okay, and then you have to do all this stuff to get to that. So we'll start that tomorrow. I'll spend a couple days on this, probably at least Monday, Tuesday, and then we'll get into regression and correlation. Next week will be a weird week, okay, because of, I think there's 2 3-hour delays and a 2-hour delay. So it'll seem like a very brief week within the classroom.